Hello developers, let's start developing. My name is Veko and today we're gonna be taking on the 21st Advent of Code 2021 task. So, I've read through the task and to be honest I have a strong feeling, not knowing the second part, that this is gonna be a two-parter video. First of all, we're gonna need to play a certain die game. Nice game of Dirac dice, whatever that is. So we have an area of 10, a loop of 10 fields, 10 spaces marked 1 through 10 clockwise. So we are not 0 based, we are 1 based. Each player starting space is chosen randomly, and then for this part of the thing we have a deterministic dice. What does that mean? That we have a 100-sided die that will always roll successive numbers. So the first roll will roll 1, the second one will roll 2, the 90th will roll 90, the 101st will roll 1, and so on and so forth. So basically you roll the dice 3 times, you add up the numbers, and then you move that many fields and you get that many points. Once one of the players reaches at least 1000, the game stops. So we just need to implement the game, we need to simulate the game. From what I've seen of the puzzle input, it's trivial, so I don't think that we're gonna need to read any files this time. We're just gonna say, well, return 4 and 8, and that's what we have. But I will change this so we're not using an array of numbers as our input, we are using a tuple of numbers. So this is an array with exactly 2 values. Yeah, and that's everything is nice, but the type inference doesn't work for this type because it says, well, I know that it's 2, but is it gonna be? Is it really gonna be always 2? I don't know. So this one way we can guarantee. So in order to simulate, we can just have some variables. Let's say the position of the first is input of 0, the position of the second is input of 1, the score of, actually I'm gonna use this. So because we're gonna have a lot of variables that are called f something or s something. The score of the first one is 0 at the start, the score of the second one is 0, and while f score is less than 1000 and s score is less than 1000, I will add a lot of parentheses so I don't make any snafu with the values, with the conditions. So we will roll the die. The die is not rolled, so it's at position 0. So we're gonna roll the die, and whose turn it is? Yeah, we're gonna use a 0 and a 1 for the turn. Actually, we're gonna use this. Let's call this F turn, and F turn is true. We just need one boolean because it's if it's not the first person's turn, it's the second person's turn. Does the first person go first? Yep. Okay. So we need to roll the die 3 times. And how do we do that? Well, in this case, we're gonna roll it once, twice, thrice. Of course, we can calculate these things, but let's keep to the spirit of the game. Twice is die again. Increase the die once more. And die again. And after each assignment, we can say if die equals 100, then die equals 0, because we're gonna roll it again. So these are the 3 rolls that we have, and after we have 3 rolls, moves is actually once plus twice plus thrice. So we are getting how many moves that we need to do. And actually, I'm gonna do this. So we are saying that we have, now let's do it this way. We have 10 items wrapping from 1 to 10. So that means that if it's the first person's turn, then do something else. So the position, the position needs to be increased by that many moves. And then the positions should be, we just need the last number, because if we go from 10 to 11, you know what? No, we cannot just call 10 0, because we need to increase it by that many points. But on the other hand, what is stopping us from just moving forward? We don't need a loop at all. So if you're going to the position 27, we just add 7 points. Yeah, we do that. So points is basically fpos modulo 10. Yeah, so if in the 17th position, that will give us 7, and if you're in 20th position, this will give us 0 or 10. So we're gonna use the weird thing where 0 is falsy and everything else is not. So if this thing returns 0, we're actually gonna return 10. If this thing returns a non-zero thing, 1 through 9, we are returning 1 through 9. I guess. And then we increase that score by that many, and we say it's not our turn. So let's see if you are able to guess this. Yep, you are. Okay, and now let's lock some state. Yep, and then we can do S. Yep, that one. We have everything we need, and see if this thing actually executes. And I'm gonna start it here because we're gonna have a lot of output, so we can look at it better. Where's the start? Oh, this is from another task. We run through, yeah. So let's see what happens. First gets a score of 10, then the second one gets a score of 3, then we have 14 and 3, and so on and so forth. Since player 1 has at least 100,000 points, the losing player has 4,754 points. And is that the case? Yep. One thing to see is, yeah, while it's less, so if it's equal, we're gonna break. That's great. Losing player, and the die has been rolled a total of 900 times. So we need to count the die rolls. Let's add that here because it might be useful to have some kind of helper function that will roll the die for us and increase whatever needs to be increased. But we can do this as well. Let's see this. Yep. So now we'll just get a single line of output, and we have 993 rolls. So our return will just be, oh, we're gonna need an if. So if the F score is bigger or equal than 1,000, then return S score times die rolls, otherwise the other thing, the F score times die rolls. Looks like okay. So our output is that much. Play a practice game using the deterministic 100-sided dice. The moment either player wins, what do you get? Blah 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 if you multiply the values. So we need to get our input, and our input is 8 and 3. I don't think it will be any different time-wise or processing-wise because a number is a number. And we'll get some thingy. Let's see if this is correct. Yep, that's the right answer because this is kind of trivial. Now it's time to play the real game. It's time to play the real game. And I think this might be hard. A second compartment opens this one time labeled Dirac dice. Okay, a single 3-sided dice. How do we get a 3-sided dice? I mean, we can take a 6-sided dice and paint 1 and 2 and 3 on 2 of the things, but I think that the minimum number of faces a solid can have is 4. Anyway, as you experiment with the die, you feel a little strange. An informational brochure in the compartment explains that this is a quantum die. When you roll it, the universe splits into multiple copies. Of course. One copy for each possible outcome of the die. Yeah, just like the episode of Community, so we are in the darkest timeline. In this case, rolling the die always splits the universe into 3 copies. One where the outcome of the roll was 1, one when it was 2, and one when it was 3. Great! The game now ends when either player's score reaches at least 21. Using the same starting positions as in the example above, player 1 wins in that many universes, but player 2 merely wins in that many universes. Using the given starting positions determine all possible outcomes. Find the player that wins in more universes. In how many universes does that player win? And if I'm not mistaken, I am mistaken. So this will grow incredibly quickly. So we will have to do some fancy caching, because for the first roll of the die, actually each player rolls thrice. So for the first move, when the first player does it, that can be 3 times plus 3 times 3 plus this, so we have that many options for the first turn, 27. And then we have, well, actually 27 squared. Yeah, so it will be 27 times 3. Yeah, and this is exactly 27 squared. Will it be this much? No, actually it will be quite less. It will be 3 more times, 3 more times, 3 more times. Come on. No, I want this times 3. So it will not be C1 times C1, it will be C1 times C1 that fixed the 1. So that this will also be C2 times C1, and so this is move 1, move 2, move 3, move 4, move 5, move 6, move 7, move 8, move 9, move 10. So after 10 moves, we will have this many universes, so to say, and that's a whole lot of universes. Basically, modern computers can take care of anything. My computer, so to say, can run a loop of 1 billion records quite fast, and that's about on this scale. So if I wanted to brute force this, I would be okay-ish up till 8 or 9 steps. But at the 10th move, I would just, this will get to the point when we are running quite a while. So until the 20th move, we will be 10 to the 28th, and actually if we process 10 to the 12th every second, which means we are processing 1 billion universes every second, that will still live with 10 to the 16 seconds. And 10 to the 16 seconds, so basically a billion seconds, 10 to the 12 seconds is somewhere around in the neighborhood of 30 years, I think. And we will have 10,000 of those, so this thing will take a lot of years to get to 20 moves. And I think that the game will end just about here unless we're terribly unlucky and it takes a few more runs, because you saw, let's see it on the example. So basically we will get a win here on move 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Or maybe we can brute force it if we only have 7 things. Just let's count the digits in this. And that's a lot of numbers, so we're not gonna brute force it. This is millions, this is billions, this is trillions. So we have something, we will need to loop something like, well, it doesn't really matter that this is about half, the bigger half, so to say, of the data, so we're gonna have to loop something through something like 800 trillions. So even if we manage to have 1 billion each seconds, we will need something like 1800,000 seconds, which is quite a while, and it's something like 10 days when it will get to be New Year's, and I really don't want to do that. So this the first part solved, and the second part we're gonna be solving later.